So hi everyone. So thank you, Jamie, for the introduction. So my name is Artem Aguichine. I'm a postdoc at UCSC, so about 1 hour and a half away. Thank you so much for being here, and thank you organizers for the invitation and for this fantastic event. And so today, what I want to share with you is a little bit of my research around the search for water worlds among exoplanets. So before we talk about exoplanets, let's talk about something we know and love, which is our own solar system. So this is artist's sketch of the solar system. The sizes are to scale. The distance is not that much, thankfully. So we have the Earth that is here, the third planet from the Sun. I don't know if you can see the Lick Observatory from there. Yeah, me neither. Yeah, and so we have our beautiful sun that is very warm and gives us all the energy that gives us life. And then we have the terrestrial planets, and then further out we have the gas giants Jupiter and Saturn, and then we have Uranus and Neptune. And so this is it, 8 planets, sorry Pluto. One of them we know is habitable and inhabited. Well, we are data points technically. And what about distant worlds? So right now, this is an artist rendering of 1,600 exoplanets to scale to each other, just by size, not by distance to each other, of course. And actually, the color here is meant to represent a measurement of these exoplanets' temperatures. And so once again, this is 1,600 exoplanets, and this is just 1/4 of what we discovered. We are about to reach the 6,000 discovered and confirmed exoplanets so far. And so if in our solar system we have one planet that has liquid water on its surface and that is habitable and inhabited, what about these worlds? And so the question that I am interested in, and this is my opportunity to give a little short CV about myself. So I'm interested in the study of water. So as Jamie said, I did my PhD in Marseille, France. It's a city by the Mediterranean Sea, so we have the beaches, we have wine, cheese, best place in the world, really beautiful, I love it. And there I was mostly interested in how water gets distributed in the solar system with theories of planet formation. And in 2022, I obtained my PhD, hence the title of doctor. And I've been a postdoc at UC Santa Cruz, about 1 hour and a half away from here, where I was studying exoplanets and how to find water on exoplanets. So, you know, Santa Cruz, the beaches, the sun, the wine, the cheese, best place in the world. Yeah, and of course, I cannot study water. The reason why I'm interested in studying water is because of astrobiology reasons, because water is one of these elements that is essential for life. And so in about a month, I'm moving to Ensenada in Mexico to develop a group of planetary science and astrobiology. So for those who don't know, Ensenada is in Baja California, just a bit beyond the border. It's right by the sea, so beaches, wine, cheese, best place in the world. There's a pattern here. So why water? And so today I will talk about some of the aspects of water. So the fact that it's a very common substance actually in the universe, something we don't necessarily think about. It is also essential for life, of course. And I also want to convince you that there are ways we can detect it, and hopefully we will learn that there are actually very promising prospects for life characterization. All right, so before moving to the planet, so let's take a step back and think about the composition of our own solar system. So our solar system is dominated by 2 elements, hydrogen and helium. They make up 99.9% of all the mass that is in our solar system. And then we have a little bit of all the other elements like oxygen, carbon, neon, nitrogen, and so on. So let's zoom in a little bit inside of that diagram. So as you can see, actually oxygen is kind of a common element compared to the other, to the next in line. And so the question really, what this means is that when we look at the chemical composition of objects, in our solar system. We're going to see things that are very rich in hydrogen, helium, and then the next molecule in line is going to be formed by combining oxygen and hydrogen, and this is actually water. And why not helium? Because helium is a noble gas, it's chemically inert, it doesn't like to react with other species, it prefers to stay by itself. So then after water, we form a little carbon species, so methane, carbon monoxide, carbon dioxide. These are the next molecules we're going to see a lot in planets and exoplanets. And then we have everything else. So we have neon, ammonia, and a bunch of what we call refractory elements. So these are all the constituents that make up terrestrial planets, such as the Earth and other rocky planets, Mercury, Mars, and Venus. And so what this diagram actually shows is that water is extremely common. It's everywhere in our solar system. And so let's just make a quick review about where water is located. Do you know one object in the solar system that contains water?
Mars?
Which one?
Is it Mars?
There is water on Mars, yes. Where else?
Earth?
Yeah, Earth. Very good, yeah. So, well, I have some here. If you yeah, so if you take a cut of the Earth, this is how it looks like. It has an iron core at the center with an outer counterpart. Then it has a mantle, a lower one, an upper one, and then a bunch of things with a teeny tiny little bit of water. So despite the fact that water covers about 70% of the surface of the Earth, it only represents a drop at the surface when we think about what's the total budget of water on the Earth. And so this raises the question, of course, where else there's water? Well, Mars, yes. And actually, if we make a rough estimate based on what we know on other objects, it is that all of the gas giant planets, Uranus, Neptune, Jupiter, Saturn, they contain a bunch of water. And some of that has been scattered in comets as well. And so Earth and all the other objects like Mars and also the icy moons, we'll talk about them in a second, they represent just a teeny tiny fraction of that. But of course, these objects, they are very far from the sun, they are very cold. So on comets, it's solid water, it's not a liquid. And if we were to throw some water on Jupiter, it would freeze out and sink to the bottom. So so does that mean that there is no prospect for habitability in the solar system? Not quite. There is actually liquid water on a different kind of object in the solar system, and these are the icy moons of all of our giant planets. So a few of them are Europa and Ganymede, which are two moons of Jupiter. And then we have Enceladus and Titan, which are two moons of Saturn. And so one of the interesting things is that they are extremely water-rich, but they're also cold. So on the surface, they have a very thick, icy layer, but beneath that layer of ice, there is actual liquid water. How do we know it? We've been there. Easy. So in the early 2000s, the Cassini-Huygens mission was launched and made its way to the system of Saturn. The Huygens probe was a lander that actually landed on the surface of Titan, taking very breathtaking pictures, by the way. And even more exciting, especially for the astrobiology community, the Cassini probe flew around Enceladus, and so what it found is what we call plumes, which are the water analog of volcanoes. So imagine a volcano, but made of ice and water. So plumes of water being expelled from the interior of this moon. And so Cassini flew through these plumes, measured their composition, and found that it was 96% water. And so from that, we have pretty good evidence to think that all of them are actually water-rich with all of our assumptions. And because of that, there is a new generation of missions that are planning to study these icy moons more in depth. So Dragonfly is going to, it's a car-sized drone that is going to fly on Titan because it has a very thick atmosphere, and it will measure the composition of its atmosphere. There are hydrocarbons and a lot of potential precursors, molecules that are precursors to life. And then the NASA mission Europa Clipper and the ESA mission JUICE that will arrive in about a decade to the Jovian system to study Europa and Ganymede respectively. And of course the goal here is to have some clues about potential habitability of these objects. So there is a lot of very interesting things. So when you think about these molecules that we call volatiles, they are the main components of the giant planets. They also are very common in icy moons, and surprisingly, our own composition, life, resembles that composition most than the rocky planets that are just made out of refractory rocks. And so naturally, naturally, this brings the question: what about exoplanets? We have so many of them. Can't we say something about what they are made of and what is their composition? Well, this is exactly what I want to show you here. So I cannot resist the urge to present you this very boring-looking graph, but that is actually so exciting. This is the count of confirmed exoplanets as a function of the discovery year. And so you probably heard 2022 Nobel Prize in '95 for the first exoplanet around an a main sequence star. The first exoplanet was discovered in '92, actually. And today, we're approaching the 6,000 mark. And so what you can see from the coloring here, these are the methods of exoplanet detection. And so the method that discovered the most exoplanets is transit photometry. And what is interesting about this technique is that it not only confirms the existence of a planet, but it gives a planet radius. And the second one, which earned Michel Mayor and Didier Queloz their Nobel Prize, is the radial velocity method that, among other things, gives a planet's mass. And so let's dive in and talk about the transit method. So when we think about stars, we picture these objects that are so cool. There are like balls of plasma. There is fusion happening in the core, and there are flares and magnetic fields. And then when we point a telescope at a star, this is the reality we're faced. So this is a photo of the 51 Pegasi star taken from the SIMBAD database. And you may think like, oh, okay, it's not that bad. If we just like refocus a little bit, have a bigger telescope, yada, yada, yada. Well, this is 100,000 times the size of 51 Pegasi b. So we're really nowhere close to actually discern what a star looks like. This is, of course, not the closest one, but this is the general trend. So when we're looking at stars, what we see essentially is just the light that comes from them. But astronomers are smart. They know that even with so little information, we can still do something. We can look at just the brightness of a star, and we integrate that over time, and then things start to happen. So what you see on the left is the observation of a binary system, and on the right is the brightness as a function of time. And when we do so, we actually see things happen, and the question is to explain what is going on. And so this is what gave the transit photometry method, which is one way of discovering exoplanets. So transit photometry is about looking at a star and seeing the shadow cast by an exoplanet that is going around that star. And as shown by this animation, there are two things that we obtain here. First of all, the size of the shadow can tell us what is the size of the planet. So smaller planet, smaller shadow, bigger planet, bigger shadow. So far, so good. Also, the duration of that transit tells us something about the orbit, how fast that planet is going around that star. And that is going to tell us how far the planet is from the star. There's actually a third thing we can see. I don't know if you can guess that. We don't necessarily see the spectrum from here. Something a little bit simpler. Consider the fact that the planet is in a stable orbit around the star. So what else can we measure? We can measure, so gravity is a cause for some phenomenon. So if the planet passes one time at some point, then we expect that to happen.
Size of the star?
If it has moons.
Sorry?
If it has moons.
We can look at exomoons, but we're not there yet with our technology. But that is a very great guess, yeah. I'm going for something much simpler. It's the fact that the planet will have multiple transits because it's in stable orbit. So if we see one transit, we can actually see many. We just have to time it correctly. And so this is exactly what happened with the system, with the TRAPPIST-1 system, which is about 100 parsec from us, so 30 light years. And the star was observed for multiple campaigns. And what you see at the bottom left here is 1 week of observation of that star. And what you see in this figure, animation represents the brightness of the star as a function of time. And as planets of the TRAPPIST-1 system pass in front of it, they cast shadows of different depths, and also shadows of different duration with different periodicity. So we can actually look at them, unfold them, and look at them a little bit more into details. So we have planets, 7 planets, B, C, D, E, F, G, and H. And you can, and these curves, they are all individual transits of these planets. So already what you see is that different planets have different sizes of shadow. And that does mean something about their actual physical sizes. And they also have different durations that is related to how fast they were going, and hence how is their separation from each other. And so all of these properties, they allow to say something about what these exoplanets actually are. One of my favorite data sets from the TRAPPIST-1 system is this triple transit of planets C, D, and C, E, and F. So at first, 2 planets, the green and the pink one, enter in the disk of the star, and so they cast a bigger shadow. Then about half an hour later, the third planet enters also this plane, making the shadow even bigger. And then the exoplanets, they start to go out one after the other, and we recover the full brightness of the star at the end. Isn't that exciting? I mean, I'm excited. So, yeah. One of the reasons this system was of great interest for the astronomy community is that out of all these planets, 3 of them are in the so-called habitable zone. They can have liquid water on their surface if we make some assumptions. And so, of course, this is why we are interested in studying these systems a little bit more. And so, once we can measure the sizes and the periods of exoplanets, what I'm showing here is an animation of how many of the sizes of planets as a function of their period through the years, so from 99 to 2025. And this is how fast this diagram is getting completed. And so just to make it a little bit more intuitive, Of course, shorter orbital periods, that means the planet is very close to its star, so it's very hot. And if it has a very long period, if it takes a long time for the planet to go around its star, then it's going to be very far and very cold. And you have the planets of the solar system for reference. They are kind of outliers in this graph. And what you see in this graph is two distinct populations. The top one, which is about Jupiter size and very hot, hence the name hot Jupiters, very creative astronomers, good job. And then, surprisingly, we don't have many of these Neptune sizes, we don't have many of these terrestrial planets, but we have a lot of something in between. And these are, we call them sub-Neptunes because they are smaller than Neptunes. And these ones, as we'll see, they are very interesting targets because they could have very big reservoirs of water. All right, so this is how we measure an exoplanet radius. What else can we do? So to measure other physical properties of exoplanets, we can use a method called the radial velocity method. So maybe something that you have heard in astronomy talk, but more about the cosmology, so not the planets, but more like galaxy, is a concept called redshift and blue shift. So this is when an object is moving and our perception of that object gets distorted. So you felt that phenomenon when you heard an ambulance going by you. When it approaches you, the pitch is slightly higher. When it goes away, the pitch is lower. And so the same thing happens with light. When objects move closer to us, they appear bluer. When they move away from us, they appear redder. And this is a real effect that we can see and measure. And so once again, we can only see the brightness of the star, but what we actually observe is that stars get redder or bluer periodically, and the reason for that is planets. And so just to illustrate that with an animation, again, think about the telescope that cannot see they cannot see the planet, but we can see the star and look at its light, and it is actually possible to measure how much redder it gets or how much bluer it gets as the planet revolves around that star. And this is the method that Michel Mayor and Didier Queloz used in 1995 to discover the first exoplanet around the main sequence star, 51 Pegasi b, because letter A is for the star, so the first planet is the planet B. And this is measurements of the radial velocity. So this is just a measurement of how fast the star is moving away from us and back to us. It's just a speed. They managed to measure that velocity and infer that there is actually an exoplanet around the star. Not only that, they actually measured its mass. It's about Jupiter mass. And once again, this method has been perfected over the years. And so this is where we are now. So these are the masses of exoplanets as a function of discovery year. And you can clearly see the trend of decreasing mass because we've improved our techniques, we've improved our telescopes, we understand better how to look at different systems, and we have finally reached this 1 Earth mass limit. We are finally capable of measuring the masses of objects that are the same mass and size as the Earth. We're there to find Earth analogs. But let's not talk about the error bar on that one. All right, so we have the mass, we have the size, and then we have the density. And I'm from a physics background, so for me, density means a lot. And I actually have a little experiment that I wanted to conduct to show you that anyone here can be an astronomer. So can I get 2 or 3 volunteers to make a little experiment on how do we understand composition from mass and radius? Yes, please. 1 and 2 in the back. Yeah, with a white t-shirt. Awesome. There is a second experiment, so if there are other volunteers, you will have your chance. Yeah. So I really love kombucha. So these are filled with, so by the way, can I ask your names, guys?
I'm I'm Rekha Rao from San Jose.
Rika Rao,
Yeah.
nice to meet you.
I'm Talha.
Taha.
Yeah.
Okay, nice to meet you.
Nice to meet you.
So I have 3 bottles, and what I will ask you is to just lift these bottles. You can lift them 3 times, and just the first 2. And I want you to tell me how much water do you think there is inside? Just by lifting, no shaking, no stirring, just lift them up and down.
I think this has about half and this has maybe a quarter.
Okay, would you like to repeat the experiment?
This from the top.
This one may be like a fifth, and this one may be a quarter, I think.
Okay, yeah. So what if I told you that one of them actually doesn't have water? Now remove all the rules. Can you figure out which one has water, which one doesn't have water? You can touch them and lift them and. So what?
This one doesn't have water.
Okay. Can you repeat the experiment? Can you confirm that?
I think I would agree with that, yeah.
Okay. Did you notice what happened? How they went from experiment 1 to experiment 2? Yeah. Why is shaking helpful?
So you can hear it maybe? You can feel it.
Yeah.
You can feel it move.
Yeah, you can feel it move. So so the ball in the middle actually is half full, and the second one is filled with sand to a quarter. And so what this experiment shows is that without any a priori knowledge, just by looking at the size of this bottle and by looking at its weight, you're capable of determining what it's made of, right? Now, can we do the same with the third bottle? Can you figure out how much water in that bottle there is?
Shake it or just.
Can you just lift it for now?
I don't know. If it's water, it's like full.
Okay.
Yeah.
Do you mind trying?
I don't know. Could be anything.
Yeah, I'd say it's full.
It's full? Okay. So this was a trick question, and you were actually right. This is not water. This is filled with sand, once again.
That's why I said if it's water, it's full.
Yeah. So what that tells us is that we're capable of, when we see an object, and we as humans have a very good sense of density of objects. We're very good at sensing the density of water. When you lift a cup of coffee or a cup of tea, you are very prepared to a specific weight. And so thank you very much. Let's applaud our volunteers for this first experiment. So because we have a good understanding of how density works, we are capable of determining compositions. And this is what brings me to the fabulous world of interior structure modeling. This is what I'm doing on my everyday basis. It's when astronomers, or more precisely theorists such as myself, predict the composition of a planet's interior. And let's not talk about what is crossed in red. So what is interior structure modeling about? So let's start with something that we know, objects in our solar system. So we have 4 terrestrial planets, Earth, Venus, Mars, and Mercury here. And then we have 4 moons, Ganymede, Titan, Callisto, and Moon. And I have the mass on the x-axis and the size on the y-axis. So based on density alone, we can make theoretical predictions. So these 2 lines are theoretical predictions of objects that are Earth-like in composition and objects that are 50% water in composition. And so based on that line, we see that Earth, of course, is made of Earth-like material. So far, so good. Venus is kind of the same. Mars has actually been found to be quite oxygen-rich in its mantle, and so it's a little bit bigger than, it's a little bit puffier, a little bit less dense than an Earth-like composition. The opposite happens for Mercury because it's iron-rich. Iron is very dense, and so Mercury is a little bit smaller for its mass. The Moon is mostly made out of the material of the Earth's mantle, so it's depleted in iron, and so once again, it's a little bit higher than that green line. Now, when we look at the icy moons, they are actually really close to that 50% line. And this is one of the first arguments that we had back in the 80s when the Pioneer 10 and 11 missions measured their masses, is that they are very low density, so they must be water rich. Okay, and what about exoplanets? Well, here they are, a few of them, so one here, a few there. Am I forgetting something? Oh, right, the most common exoplanets, sub-Neptunes. Here they are. So actually, when we extrapolate that knowledge to this population of sub-Neptunes, we realize that a bunch of them are aligned on that Earth-like line. So far, so good. This is kind of reassuring. And then we have a bunch of them that seem to be adjacent, very close to this 50% water composition. And now, and so this is one of the arguments that we can use to say that these objects, they contain big amounts of water or something else that is lighter. Now, one of the things is that this extrapolation assumes that the water is liquid or solid, just like on the icy moons, which are very hot, very cold. Exoplanets, on the other hand, are actually very cold because they have smaller periods. They are much closer to their host stars. And so what happens is that water cannot be present as a liquid or a solid on the surface. And this brings me to one, I want to open a parenthesis about some atmospheric considerations, is that imagine that we take the Earth and we increase the temperature a little bit. Well, what is going to happen is that water is going to evaporate because the temperature is going to be higher, so the vapor pressure of water is going to make water go into the atmosphere. Now, the thing is that water is actually a strong greenhouse gas. So it's going to increase the opacity of the atmosphere. And if the opacity of the atmosphere increases, then that means the greenhouse effect is stronger. And this is a self-sustaining loop that can, in some cases, lead to what we call the runaway greenhouse effect. This is a greenhouse effect that sustains itself and makes the entire liquid ocean evaporate. And that leads to the formation of steam atmospheres. And so contrary to what we see in the solar system, when objects have an icy shell or liquid water on their surface, this represents only 3% of the exoplanets based on their period. Most of them actually develop, at least if they exist, steam atmospheres, and therefore we call them steam worlds. And these are some of the objects that I study, and I want to tell you a little bit more about them. But to understand what's happened, let's talk about the phases of water, and I would like to introduce a guest, Walter, the water molecule, that can exist in various states, just like us. If we're being put under pressure or under temperature, we behave differently, and so does Walter. So Walter can be in liquid state. This is a natural state for liquid water on Earth. It can be in vapor state or solid state. And each of these states are determined by some different arrangements of water molecules. And so let me run a little bit through that diagram. So you are about here, 20 degrees C or 68 Fahrenheit, 1 bar pressure. And if you put some water in a boiler and you get a little bit hotter, you reach this 100 C limit, and this is what we do when we make tea. If we go in the opposite side, then we reach the solidification line, and then water becomes icy, and we can use that in our margaritas or iced latte. And then there are a couple more interesting points, which is the triple point here, where water can be in all three states, which is called the triple point, and then we have the critical point all the way up there. And so just to give an approximate ballpark of what naturally can happen on Earth is that the atmosphere has a little bit of vapor. It's typically in that range. And the oceans, they are all the way up here and extend much further beyond. And so scientists were like, yeah, no, this is a too small diagram. Let's actually build what we call a diamond anvil, compress some water, put it at pressures, that are 3 million times the pressure of the atmosphere and build this massive phase diagram of water. So you are here in the liquid region, and if you try to go a little bit higher, and you can explore this phase diagram, but if you compress water hard enough, you make ice again. So hot ice, actually. So this is from Wikipedia. You can grab that water phase diagram anytime you need. And so just for reference, this is naturally occurring state for water on Earth. So the oceans, they get about that high at the 10 kilometer depth, and 3 million atmospheres, that's about here where we conduct these experiments. And so why is that useful? That is actually useful for our icy moons. So we can visually represent the path of the water from the surface here, the icy shell. We can go deeper, deeper, deeper inside of the planet until we reach that transition between ice and liquid water, and then we can go even further down, and this represents the pressure and temperature at the bottom of the planet, and sorry, of the moon. Now, did I say that physicists are crazy for doing these phase diagrams? Sorry, physicists are insane. So about 1.5 hour drive north from here in the National Lawrence Livermore National Laboratory, they create experiments of nuclear fusion where they shoot massive lasers recreating the conditions at the center of the sun to probe the properties of materials at such high pressures and density that we find in the gas giants. And when they do that, they discover that water, this nice and well-behaved substance, can actually take very exotic forms. And one of them that is actually pretty neat is what we call superionic ice. So this is when the oxygen atoms in the water, they form a lattice structure that behaves like a solid. And the hydrogen atoms in water behave, can flow like a fluid. And they are conductive. So it's like a solid and liquid at the same time, and it can conduct, and it can create magnetic fields. It's weird. Yeah. And this thing, we actually expected to find that inside our ice giants, Uranus and Neptune. So Uranus and Neptune, they have very thick, mostly hydrogen envelopes here that extend very, 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 very deep here. And then here there is some water, if you can call that water anymore, but well, I guess so. And it's where we have the beginning of a water ocean. I mean, I don't know what you call that at this point, but hey, technically water, right? And at these conditions, we're again much further than with pressures much bigger than the center of the Earth, temperatures that are reaching the temperature of the surface of the sun. Pretty crazy, right? And our exoplanets, even hotter. And so once again, what do we mean when we talk about these steam envelopes? It's so all of these are individual exoplanets that have been modeled by me, actually. And so what you see here at very low pressures, this is a steam atmosphere because we're located in the gas phase. Then water becomes supercritical, and then it turns into plasma, whatever, sometimes superionic fluid. We just don't get them anymore. They're crazy. So whenever you see these exoplanets, just remember that astronomers are crazy and they have crazy theories. But this supercritical water, this is actually my favorite state of water. What is this exactly? So the supercritical state is a very interesting state where water loses its surface tension. So when you think about when you boil water at standard in your kitchen, what you expect to happen is that the liquid gets evaporated until everything goes into the vapor phase. When the liquid to supercritical phase transition happens, the two layers actually lose their distinction, And at some point, we cannot make the difference. And there is this very cool experiment that shows the phase transition of CO2, carbon dioxide, from this liquid and gas state to the supercritical state. And so if we look at it, so we're starting to heat it up, and then instead of evaporating, the surface just disappears between the two, and we can no longer make the difference between what is the liquid and what is the gaseous. And then if we wait a little bit until the experiment, when they recondense that, this is what happens, is again, the material slowly recovers its surface tension, and condenses out as a cloud, and we recover the standard behavior of water, liquid, and gaseous. So how realistic is that? Like supercritical weird planets, does that even exist? Well, actually, yes. In our solar system, Venus. Venus is supercritical CO2. So if you look, the temperature on the surface of Venus is about 800 Kelvin, so that would be about 500 Fahrenheit, I guess. And the pressure is 100 bars, so 100 times the pressure of Earth's atmosphere, and that puts CO2 in supercritical state. And in 1982, Venera 13 or 14 missions actually landed on Venus and took photos from the surface, and this is what they saw. So this is an actual photo from the surface of Venus. The probe survived for about an hour in these harsh conditions, but they took these amazing photos that we can now use for ourselves. All right, and so when we consider exoplanets as supercritical water, steam interiors, this actually changes our interpretation of which exoplanets can be full of water. So they may not be habitable because the water is not liquid, but there is a bunch of water nonetheless inside. And we can do more crazy things like studying their evolution. And so this is some of my most recent research that got published a month ago, last month, is that planets, they form very warm and they lose that heat over time. And so we really can simulate how these objects behave. All of this based on just one single measurement of mass and size. So I gotta be honest that sometimes even for myself, I'm like, am I really doing science or am I doing something a little bit crazy here? Is there an actual way of getting the composition of a planet? Actually, well, think again about transient spectroscopy. We're looking at the size of a planet, and we get some information from that. What if we try to repeat that experiment at different colors? And this is exactly what some people did back in the day. So this is a figure from 2007 where a study led by Giovanna Tinetti measured the size of a planet at different wavelengths. So these are different colors, so to say. And they noticed that the radius is different at different colors. Why is that? Do you have any guesses? Yeah, correct. This is because of the atmosphere. Imagine a planet with an atmosphere where where different components of the atmosphere only absorb the light in a different wavelength. Then what we're going to observe is a planet that is bigger in some colors than the others. And this is what transient spectroscopy is about, is we're looking at the shadow out at different colors. And this is exactly the same phenomenon as when we look at fireworks and we see different colors of these fireworks. It's exactly the same principle. And so this was exactly the conclusion of this study from 2007, where all of these points, this blue line, this corresponds to the color of water in infrared. And so this was one of the first detections of water as vapor in the atmosphere of a planet. We've been waiting for it for a very long time. It took 10 years, $9 billion, but we finally got it. You know what I'm talking about, the James Webb Space Telescope. It does the same thing, but more. More points, more precision, more everything, and this is what we get. This is the transit spectra of the exoplanet WASP-39b, just in the near-spec prism wavelength range. And this is the planet size as a function of the color, and we see sodium, water, carbon monoxide, carbon dioxide again, because it's a very strong absorber, and then sulfur dioxide. We are actually seeing the different molecules, the different species that are present in the atmosphere of these planets. Now, one thing to keep in mind is that this is again a mass radius figure, is that WASP-39b is a Jupiter-like planet. It's very big, very hot, and so it has very big features. We can see the spectrum very well. Sub-Neptunes, they are smaller, they produce lower features, so it's a lot harder to see these features, but we have some outliers. And this one, you may have heard of it, K218b is a sub-Neptune that is quite cold for a sub-Neptune, and it's really this puffier analog of Earth. And it has the same surface temperature as the Earth, and it has been theorized to have some oceans in its interior. And when we looked at this planet with JWST, this is the spectrum that we saw. We see methane, questionable detection of carbon dioxide, and confirmation of methane again at longer wavelengths. And here you also see this DMS molecule. So this is a molecule produced by marine life on Earth that could potentially hint to be at signs of life. It is a potential biosignature. So this molecule, you actually know it because this is the molecule that is responsible for the smell of the sea. So now, just one warning is that detection is actually not statistically significant. So we're not there yet. We have not confirmed that there is life on an exoplanet, but we now have the tools for that. And one interesting exercise to do is to actually even look at if aliens have a JWST and they look at us, what will they see? So this is the simulated transit spectra of the Earth. So we actually don't see the water because water is liquid, but we see carbon dioxide, which is a very strong absorber. We see the ozone layer, methane, and speaking of ozone, there are two special molecules here, right at the edge. They are called CFCs. They are called chlorofluorocarbons, and these were the molecules that were responsible for the destruction of the ozone layer. And this is something that we can actually detect. So we no longer talk about biosignatures, signs of life. We are talking about technosignatures, signs of technology. And I'm not fond myself of talking about Dyson spheres and these crazy sci-fi theories, but yeah, technosignatures actually could be a real thing. I hope we see civilization that survive instead of civilization that destroyed themselves, but nonetheless. So to summarize this talk, water, despite being very abundant, it has great complexity, a molecule with great complexity that can be found in many different states. And exoplanets, they represent real laboratories to explore all that different behavior. And when we think about planets in an astrobiological sense, we now more than ever we can develop strategies to find life elsewhere, not just speculate, but find them. And I want to finish on a video that will show the exoplanets discovered as a function of the year. So you have the year on top and the number of exoplanets discovered. And the size of each circle that you see is actually proportional to the planet's size. And the sound that you hear is proportional to its period. So and you have a counter here at the top. So the first one in 1992, then we have 51 peg B in 95, and then we move further. So nothing much happening in the beginning, and then it starts more and more. And in the early 2010s, we launched a mission called Kepler, and Kepler truly revolutionized our thinking. If you look in this spot, in about 2014, Kepler alone found 3,000 planets, and most of them were found by transit. And now we're in 2020. And in 2022, we reached 5,000 exoplanets. And so I really like to think that among some of them, they are maybe habitable, and I hope habited planets, and that we can find them. And I thank you for your attention. And happy to take questions.
Any questions?